Real quick, after we do these questions I already wrote, since I already wrote them, we'll do a couple questions, then we'll talk about some trig stuff, then we will keep doing more differential equations. So I want to solve these differential equations, and this was the other thing that came up in class. Someone asked about how if you had a different initial condition, does it change like what your constant value is? And the answer kind of is it depends, but her answer, which was also correct, was that if you're giving an initial condition that gives you the same line or graph or whatever, then no, it's not going to change your answer. But I came with an example that we can look at. So let's go ahead and solve this differential equation. So this is dy dx equal to 4x plus 5. This is just, I feel like, a very wordy way of saying anti-differentiate this, right? This is also what you would call a pure time differential equation, because the derivative of your function y as a function of x is in terms of just the independent variable x. So if you've got d something equal to a function with just the bottom variable in it, that's what pure time means. What it really means is it's easy to solve, right? So pure time differential equations are usually kind of the easiest types because it just means you're going to anti-differentiate whatever's over here and not have to do anything else weird. Whereas in, I don't know if it's this quarter or next quarter in 17C, but at some point when we get to chapter 7, we will see other types of differential equations that require a little more work to actually be able to solve. So we're going to anti-differentiate. We're going to get y, or if you prefer y of x, right? Sometimes we like to write y as a function of x, equal to the antiderivative. So the antiderivative is going to be 4 times x squared over 2 plus 5x plus c. And I would probably simplify this and just write that as 2x squared. So I'm going to say that y as a function of x is 2x squared plus 5x plus c. And now either one of these initial conditions is going to give me the same value for c because I worked ahead and found that these were both points on my graph. But if you're given this kind of thing, we can see that either way I do it, I'm going to get c equal to the same thing. So if I do y of 0 is 0 plus 0 plus c, but y of 0 is supposed to equal 1. So that's probably, usually it's easiest if they give you the initial condition where your input is 0, because then it's usually just saying c is equal to the value or close to it. So here I'm getting c equal to 1. But if I had not had that one, if they'd given me this one instead, it's still the same sort of work. I'm going to plug in -2. Now I have to actually calculate this. So I get 2 times -2 squared is 2 times 4, which is 8. 5 times -2 is -10. And I'm still trying to figure out what c is, even though I know it's supposed to be 1. So 8 plus -10 plus c is supposed to equal -1. 8 plus -10 is -2. So -2 plus c equals -1. Add 2 to both sides. You get c equal to +1. So if they give you different initial conditions that still correspond to the same original function, it's not going to matter which one you use. Yeah. So lastly, we should write our final answer, right? I've got the function, but I didn't actually put c in. So our final answer is going to be y, or y of x, whichever way you want to write it, is equal to 2x squared plus 5x plus 1. And that is our antiderivative of 4x plus 5 with the initial condition, either one of these, same thing. All right. So yeah, at this stage, solving differential equations really just means finding an antiderivative. Later on, it's going to mean other work also. So here is another example of a pure time differential equation. dr dt equals some function of time, right? That's why it's a pure time, because the thing over here is just a function of time. Also, just if you want to clarify, if you have the textbook and you look at section 7.1, they do kind of talk about the other types of differential equations, which are the autonomous and the non-autonomous. And those are a little more complicated, but they are different and they're harder to solve usually. So dr dt equals e to the 6t. We're going to try and figure out what r of t is. So we're going to anti-differentiate. All right, the antiderivative e to the 6t, if you remember, it's 1 over the coefficient there. So 1 over 6 times e to the 6t plus c. And honestly, it's worth doing a little mental check, right? What's the derivative of e to the 6t? Oh, the derivative of e to the 6t is e to the 6t times the derivative of 6t, right? R prime of t is, in fact, 1/6 times the derivative of this, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And oh, look, those 6's cancel out. And then the derivative of c is just 0. So you don't have to do this. I'm just pointing out that it really is what's happening, right? The antiderivative of this is 1/6 e to the 6t because the derivative of this is actually, in fact, equal to e to the 6t. That's all I'm saying there. So I'm gonna, I guess I've got enough room. So here's our general antiderivative, but now we want to solve for the initial condition. So I'm gonna plug in, and I'm gonna say that r of 0, so I'm plugging in 0 for t. I'm gonna get 1/6 e to the 6 times 0 is just e to the 0 plus c, and that's supposed to equal 4. E to the 0 is 1. So I've got 1/6 plus c equal to 4. C is going to equal 4 minus 1/6. And if you were writing this in web work, you might just write your final answer as r of t equal to 1/6 e to the 6t plus c. Even though you totally can simplify this, and I would usually default to simplifying this, if you're putting stuff in web work, you can let web work do a lot of the simplifying for you. So that's not to say I'm still going to finish this problem. Right? This feels not quite complete to me. Making this just slightly nicer, 4 becomes 24/6, and 24/6 minus 1/6 is 23/6. So I would write the final answer as r of t equals 1/6 e to the 6t plus 23/6. There's our final answer. We'll do some more of these in a second, but let's go ahead and talk about trig for just a minute, just to make sure everyone's on the kind of same page. So you are certainly welcome and encouraged to remember things whatever way is best for you. Lots of people like memorizing the unit circle. Lots of people like using these triangles. So there are 2 triangles. There is the 30, 60, 90 triangle, which you get by splitting an equilateral triangle in half. So I'm going to take this equilateral triangle, and I'm going to split it in half down the middle. And that's going to give me a 30, 60, 90, right, triangle. Or if we're using radians, which we usually are in calculus, a pi over 6, that's 30 degrees. A pi over 3, that's 60 degrees. And a pi over 2, which we usually just draw as a right angle, 90 degrees. Now, she did the sides of her triangle a little differently than I like to. She made all the lengths of the sides of the equilateral triangle 1. I like to make them 2. Either way is fine. I just find it easier if you make them 2, because if you make this bottom side 2 and you're cutting it in half, then this side here is actually 1. And then this side here, we can use the Pythagorean theorem to say that if I'm going to call this, say, the height, 1 squared plus the height squared equals 2 squared. So the height squared is 4 minus 1. So the height is the square root of 3. So that's what we're getting here. So this triangle, which I'm going to draw again, your 30, 60, 90, or pi over 6, pi over 3, pi over 2, right triangle, has sides, shortest side 1, longest side 2, middle side square root of 3. And then we can use that triangle to find sine and cosine of any angle you want. Right, sine of pi over 3 is the opposite over the hypotenuse, so it's going to be the square root of 3 over 2. Or cosine of pi over 3 is the adjacent over the hypotenuse, so it's 1/2. And tangent of pi over 6 is the, so I'm looking at that angle now, and it's the opposite over the adjacent, which is 1 over root 3, which people often rationalize as root 3 over 3. And then you can use that to find the rest of the trig function. So like so typically, just like she did in class, if I'm trying to find like secant of something, I'm really finding the reciprocal of cosine. Or if I'm trying to find cosecant, I'm really finding the reciprocal of sine. So if I was asked to find, what's cosecant of pi over 3, I would say, oh, well, that's 1 over sine of pi over 3, which is going to be 1 over the square root of 3 over 2, which you would then flip and write as 2 over root 3. And then you might rationalize it as 2 times root 3 all over 3. I think my slippers get a little warm in here. So that's kind of the basics of this triangle. You can use this triangle. You can memorize the unit circle, whatever you want. The other triangle that gets used, and I'll go ahead and flip the order. So the other angle that comes up that isn't pi over 3 or pi over 6 is pi over 4, which is 45 degrees. This one to me is the easier one. You take a square, side length 1, cut it in half. There's your 90 degree or pi over 2 radians. This angle here is pi over 4. This angle here is pi over 4. Filled in. Erase this other part. And then again, we can use the Pythagorean theorem to find this third side, which is the square root of 2. And then the nice thing about the angle pi over 4 is that sine and cosine are the same, right? Sine of pi over 4 is opposite over hypotenuse, which is 1 over root 2, which rationalizes as root 2 over 2. Similarly, cosine of pi over 4 is adjacent over hypotenuse, which is the same. And I'll just say tangent of pi over 4 is the opposite over the adjacent, which is just 1. So there's a very, very brief refresher on finding trig values of different angles. If you want more, let me know sometime, either via email or in a discussion, and I can try and write up a little bit more. So let's see. Also, I know I'm just talking at kind of a fast pace. If you have questions, don't hesitate to say a thing, but I'm just gonna keep going until you guys are like, James, hold up, I have a question. Let's see, where was I? Okay, so I was gonna talk more about antiderivatives / differential equations. So let's solve this. This differential equation I think is interesting. In fact, I'm gonna do 2 steps. So she talked about today that if your function or if your derivative is 1 over x, then the antiderivative is going to be the natural log of the absolute value of x plus c. And it's mostly because what she said, right? It's because we want the domains to match up. This function, 1 over x, has a domain that's everything except for 0. We would like its antiderivative to have. So functions and their antiderivatives can and do have different domains. Usually what is also true is that the antiderivative often has a larger or equal domain. An example she gave in class, which I'm going to kind of say backwards, is what if our derivative was 1 over the square root of x? Well, the domain of that is x being greater than 0, but not equal to, because if it was equal to 0, we'd divide by 0. The antiderivative of this is, well, let's see, this is really x to the negative 1/2. The antiderivative, I'm going to use the anti-power rule, is x to the positive 1/2 divided by 1/2 plus c, which is really just 2 times the square root of x plus c. And the domain here is just a little bit larger than the domain here. Right here, the domain is x greater than or equal to 0. So it got just a tiny bit bigger. And that is so I was looking for a counterexample of this and I couldn't find one. That doesn't mean there isn't one, but in my experience, it's generally true that the antiderivative has a domain that's always at least as big as the original function, if not larger, like in this example. So that's why here we really want the antiderivative to be the natural log of the absolute value of x, so that the domain is at least as big as the domain of the original function you're antidifferentiating. That's kind of the whole story there. Also, it is literally true that the derivative of the natural log of the absolute value of x is equal to 1 over x. We're not just throwing the absolute values on because we want the domain to work. The derivative of this is also actually equal to this. Let me show you, just in case you don't believe me. So the problem with an absolute value, this is probably always true about an absolute value, is that absolute value function is always a piecewise function. So this natural log of the absolute value of x is really 2 different functions depending on if x is positive or negative. It's the natural log of x if x is positive, just like it would usually be. But if x is negative, well, we can't take the natural log of a negative number. We have to change that negative number into a positive number by making it negative x. I know it sounds like I'm making it negative, but if x is negative, then negative x is positive. And now let's differentiate this. So let me call this, sure, this is y. So then the derivative, well, what's the derivative of the natural log of x? It's 1 over x. Now, what's the derivative of the natural log of negative x? Well, the derivative of the natural log of some stuff is 1 over the stuff, but what do I have to multiply?
Negative 1 over negative x.
Sorry, my sound was not turned up very loud. What'd you say?
Negative 1 over negative x, so it's 1 over x.
Exactly. So look, no matter if x is greater than 0 or x is less than 0, the derivative of the natural log of the absolute value of x is equal to 1 over x. So it really is true that the antiderivative of 1 over x is the natural log of the absolute value of x. Great. Yeah. The other question I wanted to ask you about before I did that, I keep grabbing this. I'm going to get rid of this eraser. It's not the best eraser. It's meant for a chalkboard, I think. So, yeah, what if I wanted to find, what do we got here? Sorry. So if I had, say, 1 over 4 plus 3x, that's my derivative. I want to find the antiderivative. Well, I'm pretty sure it's going to be kind of like the natural log of the absolute value of 4 plus 3x. But I'm missing something. And I know I'm missing something because if I take the derivative of this, the derivative of this is going to give me, so again, the derivative of the natural log of some stuff is 1 over the stuff times what?
The derivative of the stuff.
Right. I don't have a times 3 up here. So since I don't want there to be a times 3, I need to divide by 3. So the antiderivative of 1 over 4 plus 3x is 1/3 natural log of the absolute value of 4 plus 3x. And we're seeing, just like with the e to the 6x, that when we antidifferentiate, we end up dividing by that coefficient of x. And that is a very common theme. So yeah, so here, this is our antiderivative. 1/3 natural log of the absolute value of 4 plus 3x plus c. Yeah, it's kind of neat. I think there's something else I want to say about that. So I'm going to actually give you a minute to work on a problem. I'm going to use the restroom. So here is my derivative. dy dx is equal to 1/2 minus 5x. I want you to find the antiderivative. And then I'm also going to have you do this one. Your derivative is 1/1 plus x squared. Find the antiderivative. I'm going to go use the restroom real quick. I'll be right back. Ooh, ha, ha, ho, ho. Just stub my toe. All right. So hopefully that was enough time. So the antiderivative of 1/2 minus 5x is going to be the natural log of the absolute value of 2 minus 5x plus c. But what do I guess I should ask, what do I need to divide by?
-5.
Yeah. So you could write divided by -5, or you could write times -1/5. Right? Either way is perfectly fine. For this one, I'm not going to let you fall into the trap, or I'm not going to let you express it. People often mistakenly say that the antiderivative is the natural log of 1 plus x squared, but we know it's not. We know that it's the arctangent of x, or if you prefer, the inverse tangent of x. So you only get a natural log essentially if your denominator is a linear function of x. So for example, this is kind of general, if your dy dx is 1/mx plus b, right, a linear function of x, then your antiderivative is 1/m times the natural log of the absolute value of mx plus b plus c. Always works that way. And for other things that aren't linear, you have to do something else. Okay. All right, other things on my agenda here. Let's take a look. Oh yeah, let's do some more. Let's do some more differential equations with initial values. So let's say we have df d theta equal to. I'm gonna. Oh, that's a good idea, James. Yeah. Let's say it's secant squared of theta plus, sure, sine of 2 theta. And we know that f of theta is, f of theta. We know that f of pi over 4 is equal to 3. This should work out all right. Maybe, I don't know, we'll find out. So we have to anti-differentiate this. Or so I just want to remind everybody, right? People would probably phrase this as solve the differential equation. But really, at this juncture, that just means we are saying, oh, well, the derivative is equal to this, so the function is equal to the antiderivative of this. So I want to find f of theta. So we're looking for a function whose derivative is secant squared. That's tangent. I will say, I really did like that Karana in class today said that that table on page, I forget, I even wrote it down on page 308, that you don't have to memorize that table because you already know it, which I think is really good to point out, right? This table on page 308 with all the antiderivatives on it, right? If you know a derivative, you know the antiderivative of the result. So I know the derivative of tangent is secant squared, so I know the antiderivative of secant squared is tangent. Now for sine of 2 theta, we know it's going to be something like negative cosine, because we know the derivative of negative cosine is equal to positive sine. But we have to be a little extra careful here. So it's going to be kind of like negative cosine of 2 theta. But again, we're running into that same problem where if we take the derivative of this, we're going to end up multiplying by that coefficient right there. So we need to account for that by dividing by 2 or multiplying by 1/2. Are there questions about this? Plus c. And now we're going to plug in pi over 4 to figure out what the constant is. So f of pi over 4. This problem turned out much better than the one I had originally written. It's good. So f of pi over 4 is going to be tangent of pi over 4 minus the 1/2, so it'll be fine. Minus 1/2 cosine of 2 times pi over 4 plus c, and that should equal 3. Okay, tangent to pi over 4 is 1. Cosine, so 2 times pi over 4 is pi over 2. For pi over 2, you actually can't use a triangle, even though it's an angle in a triangle. You have to use the unit circle. So here is my very, very abbreviated unit circle. And here are what I often refer to, it really bothers my wife when I say this, the 4 corners of the unit circle. I know circles don't have corners, but it's much easier than saying the 4 cardinal directions of the unit circle or whatever. So we've got these 4 points, and the coordinates are 1, 0, 0, 1, negative 1, 0, 0, negative 1. And the angles are 0 radians on the positive x-axis, pi over 2, positive y-axis, pi, 3 pi over 2. And then all the way around is also 2 pi. The x coordinate is the cosine value of that angle. The y coordinate is the sine value of that angle. So if I'm looking for cosine of pi over 2, I'm looking at this angle, which has an x coordinate of 0. So this whole thing is a big 0. So 1 plus c equals 3, so c equals 2. And then we should write our final answer. So it's often, I've definitely seen students make the error of stopping here. Well, you've done all the work and you've really found everything you need to find, but you're supposed to write the final answer as f of theta equals tangent of theta minus 1/2 cosine of 2 theta plus c, which is 2. That should actually be what our answer is. Right? When we're solving a differential equation, the answer we're looking for is the function that if you take its derivative, you get the derivative that you're supposed to get. All right, what else do I have here? Lots of fun things. Sure, how much time? Okay, all right, I got a decent amount of time. Yeah, let's do that. So hopefully you guys are all finding this very illustrative and helpful. I feel like there are a lot more people enrolled in this class that are not here today, which is okay. I'm just surprised that there's only 7 people here. I'm glad you're here. Thanks for coming. I'm wondering where all your classmates are. All right, maybe they're in office hours. I don't know. Let's see. What was I going to do? I was going to do, let's let's try this one. So let's solve the differential equation. What have I got here? dy dt equal to 1 over 3 times the cube root of t with the initial condition that y of 8 is equal to 5. Sometimes people will write the initial condition like this, or sometimes they'll even be nicer and say that y equals 5 when t is equal to 8. Right? This makes it very explicit. Oh, I'm plugging in 5 for y and t for 8. This makes it a little bit less easy to see what's supposed to go where, but it's not like super challenging. But first things first, we have to figure out what y the function is. So I'm going to anti-differentiate this. Well, actually, I'm going to rewrite it before I anti-differentiate it because this does not look particularly helpful. I'm going to rewrite this as put my 1/3 coefficient, and then 1 over the cube root of t, I should rewrite not as 1 over t to the 1/3, but as t to the negative 1/3. That is definitely the way we want to rewrite it. And now we're ready to anti-differentiate it using the power rule. So my function y as a function of t is going to be constant multiple hangs out. The antiderivative of this is going to be, let's see, so I have to add 1 to the power. It's t to the 2/3 divided by 2/3. I guess I could have flipped and multiplied, but I didn't. So rewriting it just a little bit, I've got y of t equals 1/3 times 3/2 times t to the 2/3 plus c. So the 3's cancel here. And before plugging in my initial conditions, I can write this as y of t equals 1/2 t to the 2/3 plus c. And now we're going to plug in that y is 5 and t is 8. So y of 8 is 5 and t is 8. So I get 5 equal to 1/2 times 8 to the 2/3 plus c. Right, 8 to the 2/3. So that's the cube root of 8, which is 2, and then squared, which is 4. So this is going to be 5 equals 1/2 times 4 plus c. 1/2 times 4 is 2. 5 minus 2 is 3. So 3 is equal to c. And so our final answer is y of t equals 1/2 t to the 2/3 plus 3. Let's go ahead and let's do this one. So let's look at a double derivative one. So let's say our second derivative, which we write as f double prime of x, is equal to 24x squared plus 6x minus 10. And so if we're being asked to find the original function, we have to be given, like she was saying in class, we have to be given 2 pieces of information. If you know just one piece of information, one initial condition, we're not going to be able to figure out what the constants are. So the 2 pieces of information that we are given here is that f of 1 is equal to 3, and that f of 2 is equal to 29. And we want to find f of x. And of course, we're going to start by anti-differentiating. We're actually going to anti-differentiate twice. So the first antiderivative is going to give us f prime of x. Right, when you anti-differentiate a second derivative, you get back to the first derivative. So let's see, I'm going to get, again, these are just power rules. So I'm going to do 24 times x cubed over 3 plus 6 times x squared over 2 minus 10x plus the constant c. And normally I wouldn't really worry about simplifying too much, but since I want to take another antiderivative, it really is in my best interest to simplify this as much as possible. So I'm going to rewrite this as, let's see, 24 divided by 3 is 8. 6 divided by 2 is 3. And yeah. So now we're going to antidifferentiate again. We're going to get f of x equal to, so I'm going to get 8 times x to the 4th over 4 plus 3 times x cubed over 3 minus 10 times x squared over 2. Now, I will say, if you're doing this problem, you probably would, if I were really kind of doing this problem faster, I would have been like, oh, 8x to the 4th over 4 is just 2x to the 4th. And this is just x cubed, and this is just minus 5x squared. So I think it's natural to do those simplifications right away. And then we're going to get the antiderivative c is c times x plus another constant that we can call anything except for c. I'm going to call it d, or sometimes k, but right. But those can't be called the same because we don't know that they're the same. They're probably not the same. So let's simplify this. Here's what we've got. We've got f of x is equal to 2x to the 4th plus x cubed minus 5x squared plus cx plus d. And now our job is to plug in these two pieces of information and solve for c and d respectively. I guess I'm going to need the other side of the board. Let's see, what did I have? F of x equal to 2x to the 4th plus x cubed minus 5x squared plus cx plus d. And I had that f of 1 was equal to 3 and f of 2 was equal to 29. I think that's all right. Let's double check. Yep, looks good. So then we're just going to plug in. So from here, f of 1 is going to be 3. So I'm plugging in 1 for x. I'm getting f of 1 is 3. And on the right hand side, I'm getting 2 times 1 plus 1 minus 5 times 1 plus c times 1 plus d. And we can't solve for c or d yet. So let's plug in this one. So f of 2 is 29. So plugging in 2 for x, okay. So f of 2 is 29. It's going to equal 2 times 2 to the 4th, which is 2 times 16, plus 2 cubed, which is 8, minus 5 times 4, which is 20, plus c times 2, plus d. And there's a lot of things you could do, right? You could solve for d. Probably the easiest thing is to subtract the equations from each other, but let's simplify this first one. So the first one is 3 equals 2 plus 1 minus 5 is negative 2 plus c plus d. So 5 equals c plus d. And we can solve for d and say d equals. Oh, excuse me. Sorry.
That's you.
Thank you. So we can say that d equals 5 minus c. And then we can plug that in for d right there. So then I'm going to have, in this equation, 29 equals 2 times 16 is 32, plus 8 minus 20 is negative 12, plus 2c plus 5 minus c. And then we can solve for c. So I'm going to have, let's see, 32 plus negative 12 is 20. So I've got 29 equals 20 plus 2c minus c is c plus 5. So subtracting 25, I get c equal to 29 minus 25 is 4. And then d equals, this is one of the advantages of doing it this way, where you solve for one in terms of the other and then plug it in, is that once you find the first one, then the second one is super easy to find. It's like, oh, d is 5 minus c, so d is going to be 1. And then we write the final answer, which is f of x equal to 2x to the fourth plus x cubed minus 5x squared plus 4x plus 1. That's our actual final answer. Let's look at this question. Where'd you go? Sure. So this is a question from the textbook. It is question 41 from section 4.6. So here is the setup. A culture of bacteria initially has 25 cells. And T hours later, increases, meaning the number of cells increases at a rate, this is kind of a crazy looking rate, at a rate of 3.4657. These are not the nicest numbers. Times e to the 0.1386t bacteria per hour, or bacterial cells, whatever you want to say. Okay. Find the population size after 4 hours. Okay, so this is an initial condition differential equation problem, just with a lot of words. So there are two things to be aware of. One, a culture of bacteria, yeah, I guess that's what I said, initially has 25 cells. So if we're going to say that, I don't know, if y of t equals the number of cells at time t, then we have an initial condition. We know that y of 0 is equal to 25. Great. Okay, the other thing, so that's right. That's this right here. This is your y of 0 equals 25. And then they say that t hours later, it increases at a rate of terrible number times e to the whatever times t bacteria per hour. So they're telling us a rate of change, right? They're telling us that when the time is 1 hour, for example, that the bacteria is increasing at 3.4657 times e to the 0.1386 bacteria per hour. What they want us to do with this information is to write down the differential equation. So they're telling us the rate of change of bacteria. Well, we said y is the number of bacteria at time t. So the rate of change of the number of bacteria at time t is dy dt. Right, that's your rate of change of bacterial cells. But we know what that's supposed to be equal to, right? They told us in the problem that the rate of change after t hours is this expression right here. It's 3.4657 times e to the 0.1386t. Okay, we know how to do a problem like this, right? We're going to try and find the function, and then, right, because again, right, they're asking us what the population is after 4 hours. So we can't plug in 4 for t here, because that won't tell us what the population is after 4 hours. That'll tell us what the rate of change is after 4 hours, and that's not what they're asking for. So before we can find the population, or I should say, before we can plug in 4 hours to find the population, then we have to find the equation for the population, which is what y of t is. So I've got dy dt. I want y of t. I'm going to anti-differentiate. So y, or y of t. So we've got a constant times e to the stuff. We know that when we anti-differentiate e to the stuff, or I should say, we anti-differentiate e to the something times your variable, you end up dividing by that coefficient there. So our antiderivative here is going to be 3.4657 divided by 0.1386 times e to the 0.1386t plus c. And we know this is correct because we know that if we differentiated this, we would end up multiplying by a factor of 0.1386, which looks pretty gnarly. So I believe this is set up so that this is actually approximately 25. Well, let's go ahead and check. So I'm kind of out of room, but I think it's okay to erase the problem because all we have to do now is figure out what c is by plugging in 0 for t and 25 for y. And then after we do that, plug in 4. So we're going to find c by plugging in 0, and then we're going to find how much we have when we plug in 4. So I think I'm okay to erase this. I know it always feels great. So let's plug in 0. So y of 0, which is supposed to be 25, is equal to this stuff. So it's 3.4657 divided by 0.1386. E to the this times 0 is just 1. So I could write times 1 plus c. So 25 equals this number plus c. And if you get out your calculator, 3.4657 divided by 0.1386 is 25.005. So clearly they picked the number so that it would be 25. So this is 25, which means c is going to be 0. Cool. So now we know what our equation is, right? We know that this is actually just 0. So our function, our population at time t, is given by this equation. So I'm just going to call this 25, so I don't have to write this gross number again. I'm going to say that y of t is 25, even though it's not exactly 25, it's close enough. 25 times e to the 0.1386t. And then to answer the final question, which is what's the population size after 4 hours, we're just going to plug in t equal to 4. So y of 4, population after 4 hours, is 25 times e to the 0.1386 times 4. And that ends up being, so right, you multiply these together, you do e to the that, you multiply by 25, and you get approximately 43. 43? So, someone wrote 43.5 and then wrote approximately 46, which seems wrong. So let's double check. 0.1386 times 4, e to that number, times 25 is 43.5. So I think they meant to write 44, not 46. Because it doesn't really make sense to talk about like a half a bacteria. But okay. All right, that is all the time we have for today. I hope it was illuminating, helpful. I will see you guys on Friday.
I had a quick question.
Of course, yeah.
For the initial equation or the y of t, is there supposed to be a plus 25?
No, there's not. So we got this equation for y of t. And this number here is about 20. So let me back up just a little bit. I'm going to change it. I'm going to fix it just a tiny bit. So this number I'm just going to replace with 25 because it's about 25. So we had 25 e to the this plus c. But then we have the initial condition that y of 0 equals 25. So when I plug in 0 for t, I get 25 for y. But when I plug in 0 for t, look what I get. I get 25 for y, and I get 25 times e to the 0 plus c. But e to the 0 is 1, so 25 equals 25 plus c, so c is 0.